This video is meant to give you kind of an understanding of how technology can be used to show what transformations are and how you can create them without physically doing them yourself. This tool right here is called the Geometers Sketchpad. It's actually a very neat program. You can create all sorts of objects, including all the ones we've discussed before, such as circles and even just generic polygons, just by describing how many sides you want. In this case, I'm making a pentagon. So we're now going to kind of take a look at, okay, how can this program be used to transform? Well, the good thing is that we already have one of our toolbars up here marked as transform, so it is actually rather easy to do. We're going to go ahead and translate our piece over here, and what you kind of see is that we have both a polar and a rectangular coordinate system. You're only interested in the rectangular. Okay. We want to shift it over 1 unit and up 1 unit. In this case, they use centimeters. But we can shift it even further over, and as you can see, there's kind of a shadow figure of where it's going to be. If we wanted to shift it further right, well, we just put a further distance, say 3 over. Okay. Every time we shift one more over, okay, it ends up getting further and further away. We can also shift the wrong way, okay, or in this case to the left, just by putting a negative in front of the number, just to indicate that we're moving to the left. Okay. The same thing can be done with the vertical distance, where we just make it 2 or 3 or 4 and bring it down back to 1. Okay. Now, it should be obvious that if we do this, and we give it a translation of 0 and 0, that it should line up. Our shadow object should line up with what has the cross grid on it. Okay. So we're going to do that just to verify that that's actually what happens. Okay. So we can do that with any objects. Translations aren't terribly interesting, though, as far as this goes. Translations work very easily on graph paper. Okay. But when we're asked to, say, rotate something, okay, we're actually going to create a point about which to rotate. Okay, let's actually choose this guy right here. We're going to rotate, let's choose him to rotate. We're going to rotate, and it already said it picked this as the center. We want to pick this as our center. Okay. And you can pick any of these points. In fact, you can pick the ones on the circle. Okay. So what you notice is that this object right here has shifted around 180 degrees. It has basically spun a quarter circle. We could rotate it 180 degrees, okay, and notice that has basically flipped around. Okay. 270 degrees will put it over here again. Okay. And then 360 should again give us the two objects overlaid on one another. I'm sorry, 360, not 260. Where again, it's all right back there again. But that's a rotation about a particular point. We could, in fact, let's choose different points now. Okay, let's say that we have 90 degrees. That's 90 degrees about this one. Okay, which means that every point is the same distance away that it was before, but at a right angle to where it was. So this point right here, if you were to draw a straight line between these two, would be at a right angle to its transformed point down here, and it'd be at the same length as it was before. Remember, when you do a rotation, the scale doesn't change, so all these distances are going to be preserved. They're going to be the same distance away as well from that center of rotation. Okay. If we instead choose a different rotation point, it's going to shift where we're looking. Okay. It's also going to rotate the other point that we weren't considering before. Okay. Now we have these other points that we are interested in. Okay. All of them can be rotated about. And each of those is particularly easy. The point that stays there, because notice that each time we choose one of these points, one of the vertices will always actually be at the same location. Well, that should make sense. If you're rotating about that point, it's the only one that physically does not move. Okay. So we're going to go ahead and cancel that one. We're now going to transform with a reflection. Okay. We must construct a mirror instead, basically a line before we can reflect anything. Recall that if we're going to reflect, we need to reflect about a line. So we're in fact going to make a line right here. We're going to shift everything down so we can see what happens. Okay. And then we're going to reflect, transform, reflect about that one. Okay. Notice that this point is mirrored over here. It's the same distance away. Each point is the same distance away from our reflection line. Okay. If we choose to move our line, okay, we change where our reflection ends up being. Okay. The closer we move to the other object, the closer the mirrored reflection becomes. The further away, the further the object. What happens if we, of course, tilt? Okay. If we tilt this, where the reflection ends up is dependent on the angles between the original object and the reflection line. Okay. So if we take this point and move it around, notice that this one actually wasn't part of the reflection, so he can be gotten rid of. Okay. Now, we can accept this reflection or we can just delete it. And now we're going to look at the other part, dilations. Okay? Dilations, recall, do not preserve scale. Okay, we're going to get rid of these other 2 points as well. We have our object. We can transform by, let's do both a point outside, let's say the circle first, okay, and then a point inside the circle. Okay. We're going to transform the circle by dilating it. Okay. First, let's select the circle. We're going to dilate it. Okay. About the center G. Okay. It's a factor of 1/2 what it was. Okay. When we pick the center of the circle, of course, the dilation actually shrinks about the center, such that your circle starts out here, shrinks by a factor of 1/2. That's what this ratio is. Okay. If we shift it about the side, it shrinks to 1/2 its value, but in the direction of the actual point of dilation, the center of dilation. Okay? So that point will remain fixed, but everything else will be compressed towards it. We can also make this dilation a lot bigger. Okay? We could also make it 4 times as large, for example. Okay? But otherwise, let's leave it at 1/2. So why does this one keep the circle here? Okay? Well, that point was a white area inside the circle that hasn't actually moved. It drew this piece up towards it, it drew this piece down towards it, and all the other pieces of the circle, all the other points, were drawn in the direction towards the center line. Okay? If we instead choose this guy, we can see the same thing. All those pieces were basically shifted towards this point, the center of dilation. Okay? We're going to go ahead and cancel that one now, and we're going to kind of examine, okay, how does that help us? What can we learn? Well, we've already done, there's another video regarding how you actually construct dilations, but let's show that that's true. Okay? We have a point of dilation here. We're going to dilate this object. Okay? We're going to translate it by dilating it. Okay? And we're going to say we're going to be about this point. Okay? And we're going to actually magnify it a bit more. We're going to magnify it up here. We're actually going to move the point a bit. Oops, I only want to pick one of these. Okay. And we're going to make a different object entirely, actually, to do this. Okay. We're just going to make something that is reminiscent of a quadrilateral. Okay. We transform this point by dilating it about that point, okay, and we double everything. Okay. So we now have a new object. This is the dilation of the original. I didn't want to make that point. Okay. But we can show that each of these vertices runs a straight path between the vertex it corresponds to and the center of dilation. This would be one way, again, of finding where that center of dilation is. Okay. The cool thing about this program is we can do all sorts of things. Okay. We've already said that we're magnifying by a factor of 2, so we expect the area of this to be a factor of 4 larger. The cool thing about this is that we can measure, say, the area. Okay. The area of this guy is 48.2 centimeters. We expect that to be 4 times as large as this guy. Okay. If we measure this area, okay, apparently we have to cancel out the other guy first. We're going to delete him. If we measure this area, it should be about 1/4 of that, which would be around 12, okay, which we see is correct. So we know that we have dilated correctly and that our scaling factors still apply. Okay. We also know that we can draw, okay, we can measure anything we want. We can measure distances and perimeters, but we can also display, let's see, hold on one second here, two other processes. Now, we're going to actually do a second dilation. This time we're going to make this guy even larger. Okay. And granted, of course, we should probably just use the dilation to do it, but we're actually going to demonstrate something else here. Okay. That whole dilation now, we're going to transform about this point. We're going to dilate such that we have a 1/2 factor. Oops. Right now I'm dilating a point rather than an entire thing. We're going to dilate that piece. Okay. And notice that this is 1/2. Okay. What's really cool about this program is that we can take any of these vertices, connect it to the other guy, and we can actually, without actually drawing the line, tell it to mark the vector that goes between it. And we're going to see a dotted line, as you saw, go across the dilated object from vertex to our center of dilation. Okay. We're going to do that one more time for this guy over here and this one. And again, just mark the vector that connects them. Okay. As you saw, it goes from the vector vertice to this vertex and then back to the center again. So basically, this is a wonderful, wonderful tool in order to do some of your geometry work. It's a bit late, of course, in the chapter to be starting with it, but it is an excellent tool should you be so interested. Again, the title of it is Geometers Sketchpad.